Hi, today's podcast is on titration with strong acids and strong bases. And a titration is basically taking something that you know the concentration of, you know the molarity, and you're adding it to another container where you do not know the molarity. It's not known. All right? And in a different podcast, there's M1V1 equals M2V2. That's a simple way of doing it. But today we're going to simply walk through exactly what's going on when you have a burette. This is a burette right here. And in this burette, I have sodium hydroxide. And this beaker down here, I have hydrochloric acid. Now what's that mean if I have HCl? That's a strong acid, isn't it? So I have H plus and Cl minus ions. Right? And those are both aqueous. Aqueous, aqueous. And what do I have now? I have sodium hydroxide. Right? I have hydroxide here, and I have sodium ions. And those are dissociated because it's a strong base. And what happens when I put a strong base and a strong acid together, or an acid or a base together? It's a neutralization reaction, and I make sodium chloride, a salt, and those are dissolved, dissociated ions, plus what? Plus water. And water's a liquid. Now what's true? I'm going to go ahead and get rid of spectators. This is a spectator ion, right? And this is a spectator ion. And so what do I have left? I have hydrogen left and hydroxide left. My spectators on this side are sodium and chloride. They're gone. And so what do I have left on this side? Just water. And so my nitty-gritty anionic equation is H plus OH equals water. So really, truly, when I look at this, I'm going to ignore the sodium, even though it's there. I'm going to ignore the chloride, even though it's there. And I'm going to go ahead and look at H plus and OH minus. And that's what's going on. And what we're going to do, step by step on each of these, is the little blue dots are going to drop into this beaker. The hydroxions are going to drop in there. And what happens when you put a red and a blue dot together? Oh, look, you make water. Okay? So as I drop a blue dot in, it's going to react with a red dot. It's going to make water. The red dots are going to go down, the hydrogen ions are going to decrease, and my volume is going to go up. And that changes my molarity. So when you change the concentration and you change the volume, you change the molarity, don't you? All right, now, let's go ahead and do this. First, I'm going to find the pH with no added sodium hydroxide. What is my equation for pH? My equation for pH is pH is equal to the negative log of my hydrogen ion concentration. And right here it says I'm not going to add any NaOH. I'm just going to go ahead and look at this container here and look at just my hydrogen ions that are floating around in this container. Right? I'm not adding any of this. So it's floating around in here. 0.200 molar H plus ions are here. So if I plug that in here and take 0.200 molar, I get a pH of 0.699. 3 significant figures in all these cases gives me 3 sig figs after the decimal point. That is equal to my pH. Okay? All right, next. What am I going to do now? Now I'm actually going to drop sodium hydroxide in here. I'm going to take sodium hydroxide and drop it into this container, which means my red ions are going to go down. I'm actually going to increase the amount of water in here. So what just happened? I have less little circles, and we're going to call these circles millimoles. Okay, we have molarity, don't we? What's molarity? Moles per liter? Well, what do you look if you look at this problem right here? Don't we have milliliters here and molarity? So we're going to use something called a millimole. A millimole is per milliliter, right? So my water is going to go up, and my red circles are going to go down, which is going to change my molarity. So we're going to take red and blue and drop them in. So I'm going to go ahead and get rid of them because we've made water in here. Okay. And let's look and see how many little circles we have. Well, I'm going to go ahead and take my milliliters. And it doesn't matter what you start with. You start with molarity or milliliters. I'm going to do milliliters. And I'm mispronouncing that on purpose. So you can say millimoles and milliliters. And I'm going to go ahead instead of milliliters. I'm going to take my milliliters and multiply it by my molarity. And I'm going to go ahead and get an answer of 10. So pretend there's 10 little millimole, little milli circles down in here. They're red circles. all right, before I start. Before I even add anything, that's how many little circles are in there. Now, how about hydroxide? What am I adding? I'm adding 10 milliliters of that much molarity. So 10 milliliters times this molarity. How many circles is that? That's 1 little millimole circle, right? And we'll put 0.0, but after this I'm going to drop that 0.0. Now what happens when you drop 1 blue circle into 10 red circles? That blue circle is going to disappear. And you're going to have 9 little circles left. So I have 9 little circles left, none of these left at all, and what's happened? I've made water, haven't I? Okay? So my water's gone up. Let's figure out what my water is, or what my new volume is in my container. What's my new volume? My new volume in my container is 50 milliliters to start with from my beaker, right? And there are 50 milliliters right here. And what did I do? I dropped 10 milliliters in. So my new volume is 60, right? Now, how many little circles do I have left? Well, what did we do? We dropped in 1 blue circle to a container that had 10 little red circles. So we have 9 little millimoles left. And what happens when you have 9 millimoles of hydrogen ions over 60 milliliters? That means you have a 0.15 molarity. And what's pH? Negative log of my hydrogen ion concentration. And the answer to this right here is 0.15 molar. So I'm going to go ahead and do the negative log of my 0.15 molar. And I'm going to come up with a pH of 0.82. That's my new pH. It's increasing, isn't it? It's moving further away from being an acid, more towards being a base. My first pH was 0.699. Now it's 0.82. It's shifting in this direction on my pH scale, which makes sense because I have less hydrogen ions. All right, now let's do our next problem. What do you know? You know you have 50 milliliters. I'm going to go ahead and drop that 0.0, okay? Times 0.2. That means I have 20 little circles, 10 little circles. Of red in that beaker, no matter what. And now I'm going to go ahead and drop 20 milliliters of this 0.1 molar. So what's 20 milliliters times my 0.1 molar? Well, that's 2 little circles, isn't it? 2 little millimoles. So when I drop 2 little millimoles, those blue circles, they're going to react with these. And how many red circles am I going to have left if every blue circle hits a red circle? I'm going to have 8 millimoles left, aren't I? So what just happened? I went ahead and took another blue dot and a red dot, right? And I have less in here. And I know there aren't circles on there, but you just have a picture, guys, that there's 10 red circles down here, right? There's 10 red circles down here, and there's an unlimited number up here, lots. So what's going on? How many little millimoles of hydrogen ions do I have in here now? I have 8 millimoles of hydrogen ions. What's my new volume? Well, what did you do? You added 20 milliliters to 50 milliliters, so your new volume is 70. And that's water now, isn't it? Okay. Water and some hydrogen ions floating around. But I have more water in it, don't I? Right? Okay. I have more water because for every red circle it hits a blue circle, it makes water. So this solution down here is becoming more and more dilute, and it's also having less and less hydrogen ions as they're getting used up. My new molarity is 0.11 molar, and that's 0.11 molar of my hydrogen ions. So how do I find pH again? pH equals negative log of my hydrogen ion concentration. I'm going to go ahead and put negative log of 0.11 molar, and that is going to give me a pH of 0.942. Not changing lots, but it's changing, okay? And it's going to change slowly for a little bit. So now what am I going to do? Now I'm going to go ahead and add 100 milliliters. So what's true here? In my beaker, don't I always have 50 milliliters times 0.2 molar, 10 little millimole circles. And what's true with my OH? In this case, I have 100 milliliters of 0.1. So I have 100 milliliters times 0.1 molar. How many little circles is that? That's 10 millimoles. Okay? Now what's going to happen when I have 10 millimoles of blue reacting with 10 millimoles of red? Oh, look at that. I have blue circles dripping into this red and removing them. And now what's true is I have no red circles left in there at all. All I have is water. That's it. Now, this is called a stoichiometric point. And I shouldn't be writing this in blue because that's signifying bases or whatever, but that's a stoichiometric point, or the equivalence point. And at this point, all I have in my container, I have no OH, I have no H+. All I have is Na and Cl and water. So my pH, I would have to actually graph on my graph paper, but my pH of water, because that's the only thing that's left in my container, really that has any pH, is 7. So my pH is equal to 7. Now, the equivalence point or the stoichiometric point is not always going to be 7. But when you think about it, I have a strong acid and a strong base. So when you put a strong acid and base together, their pH is close to 7. Let's take it a step further. We're going to do 2 more steps, and we're going to look at a graph, and then I'm done. So let's go back. How many little millimoles did we have in here? We had 50 times 0.2, right? Milliliters times molarity. That was 10 millimole circles. Now what am I adding? I'm adding 150 milliliters of this 0.1. So I have 150 milliliters times 0.1 molar. And that's going to leave me with what? 15 millimole circles of my blue. So if you drop 15 circles that are blue into a container that has only 10 red circles, aren't you going to use the red circles up first? So now I'm going to subtract my red circles from my blue circles. And I have no red circles left at all, but I have leftover blue circles. I have 5 little millimole blue circles left over. And what do those represent? Those 5 little millimole blue circles represent my OH minus ion concentration. What's my new volume in here? Okay, so what's this look like in here? Let me go ahead and show you. What happened? Let me go ahead and get rid of these. How'd those happen? Because I dropped blue in with the red, didn't I? Right? Blue in with the red. And for every blue and red that dropped together, I made water. What's true? Are there any red circles left in there? No, they're not. I've dripped now past that point, right? Didn't we drip past the point when they were equal? Right, they were equal here. Now I actually have more blue circles in with water. So I have a base. Okay? So what's true? Get rid of those. What's my new volume? Well, I have 50 milliliters and 150 milliliters. That adds up to equal 200 milliliters. And if I have 5 millimoles over 200 milliliters, that's going to give me a value of 0.025 molarity. And what's that my molarity of? That's my molarity of my hydroxide ion concentration. And what do I want to find? Oh, look. I want to find pH. How do I find pH if I have a hydroxide ion concentration? Well, I know that I have my hydroxide ion concentration. I know for a fact that Kw equals H plus times OH minus. Right? That's one way I can do this. Okay? And what is Kw? Let me go ahead and erase this right here. Kw is 1.0 times 10 to the negative 14th. I don't know my hydrogen ion concentration. I do know my concentration of my hydroxide ion, 0.025 molar. Right? And I want to find my H plus. So if I do that and solve, I get 4.0 times 10 to the negative 13th molarity. for my hydrogen ion concentration. So how do I do this? If I know my molarity for my hydrogen ion concentration, that's my H plus. Okay, what do I have? Negative log of my hydrogen ion concentration is my pH. And if I put negative log of 4.0 times 10 to the minus 13th, I'm going to go ahead and get a pH of 12.40. Okay? Now, you can do the same thing with 200 milliliters, which means you're going to go ahead, if you solve through all this, you should be able to solve through all this just like I did, step by step. And your pH should be, oh, you know what, excuse me, pH of that, I'm sorry, was not 12, it's 12.40, I was right, okay, sorry. So for this one, the pH should be 12.60. And if you look, what's happened to our pHs? We've gone from a pH of 0.699 in acid. We've become more acidic. We've become even more acidic. We became a pH of 7, which is neutral. And we've gone to a pH of 12.40, which is actually a base because it's greater than 7. And then your answer here for pH, right, is 12.60. So if we look at that graphically, this is what happens graphically if we add sodium hydroxide, because that's our control, right? Isn't that our independent variable? My independent variable is I add sodium hydroxide. And we measured how much we measured volume-wise, and if you notice, where's the pH? The pH is down here, isn't it? Okay, we start out with 0.699. It's right down here. What slowly happened? It slowly changed, didn't it? Slowly. Until it became a pH of around 7. Right? There's our pH of around 7, which is neutral. Right? pH paper that shows neutral. All right? And what is that called? Oh, look at that. All the H plus is equal to all the OH minus ions. And that is called my equivalence point or my stoichiometric point. And it just so happens that on this one, it's about a pH of 7. It's not always, but that's where it is. And then what slowly happened? Did we add more and more blue circles? Okay. And so at this point, all you have is blue circles. Okay. And so this is just showing the sodium hydroxide you're adding. But it becomes more of a base, isn't it? Why? Because this is the pH scale that's a base, right? This is the end, it's acid. Right, if I wanted to go ahead and do this and write in blue, or red down here, right, this is my acidic end. This is my neutral right here. And that's my base. And that's what happened. Okay, and this is called a titration curve. And if you didn't have this, you could go ahead and you could graph it. Now, I will tell you right now that when you have a strong acid or a strong base, the line leaves the y-axis very cleanly like this. That's strong. So what would it look like if I had a pH right here where I had a pH that started high and went low like this? This would be my pH. Here I would be adding hydrochloric acid. How do you know I'm adding HCl in this case? Well, what's my pH? My pH is very high here. So I must be starting with a base down in my beaker. I must have OH ions down here, right? And what must I be dripping into it? From my burette, I'm dropping in hydroxide ions. Drip, drip, drip. What happens? They make water. And slowly what happens? My pH turns from basic towards neutral, and then it becomes acidic. See that right there? And so that's what happens, and that's a pH curve. How would I know that this is a strong base? Look at the way the line leaves. Okay? So, if I have a strong base or a strong acid, the line leaves in this manner. If I have a weak base, it's going to leave it differently. If I have a weak acid, I'll show you a weak acid. A weak acid's going to leave it like this. It has a hard time dissociating. And so that's how you would know, just by looking at the graph. And that's it for right now.